We set up the problem of firm I in exactly the same way as we did for the two firms case. So the problem of a firm is identical except that now the aggregate output Q is the sum of all the n outputs. Taking the first order condition with respect to Qi, you can obtain the first order condition that looks identical to what we had for two firms case. Now, note that you have n firms maximizing on profit, and so you have n best response function given by the first order condition here. This means that we need to solve a system of n equations with n unknowns, which is tedious. So we are going to use some trick to get the equilibrium here. We can sum up n first order conditions to get the aggregate first order conditions shown here, which is a function of aggregate output only. Then you can solve for the equilibrium aggregate output cap Q star. Since the equilibrium output level is symmetric, dividing the aggregate output Q star by n gives the equilibrium output level for each firm denoted by Q star at the very bottom. Once we solve for the equilibrium output, we obtain the equilibrium profit pi star by substituting the equilibrium output into the profit function. We can see that the profit is decreasing in the number of firms n. And so the profit is decreasing in the extent of the competition. Similarly, we obtain the equilibrium price, and 1 over n plus 1 approaches 0, and n over n plus 1 approaches 1 as n increases. Therefore, we have that the equilibrium price approaches the marginal cost as n goes to infinity. Now, firms are not necessarily competing against each other. In other words, they could be colluding to extract consumer surplus. Indeed, we will see that the collusion can increase firms' profit in a static setting. But it turns out that the collusion is not an equilibrium. We will see that collusion outcome can be sustained in equilibrium once we incorporate the time dimension into the problem of firms, and firms interact over time. Okay. To obtain a collusion outcome, we first solve the monopoly problem where the aggregate output corresponds to the monopoly's output. You can easily see that the monopoly output level is A minus C divided by 2B. Now, suppose that there are two firms colluding in the market and produce this monopoly output jointly. Splitting the total output into a half gives you how much each firm produces. So just divide the monopoly output by 2. We can see that the collusive level of output is smaller than the Cournot competition level of output. You should verify that the profit of each firm is higher under the collusive level of output than the Cournot competition level of output. Now, collusion yields a higher profit to both firms, but it is not an equilibrium. We already know this because we know that the Cournot competition level of output is a unique equilibrium of the static game. The problem with the collusion scheme in a one-shot static game is that there is no credible threat that punishes rival when deviating from collusive output. Then the natural question here is what happens if we introduce time dimension to the game and let firms interact repeatedly? In this case, the firms can apply a strategy that if you betray me today, then I will make you regret by producing the competitive output level forever. we will see that this threat becomes credible under certain condition, and the collusion can be sustained in equilibrium. To see this, suppose that a firm's lifetime payoff is given by the sum of one-shot gain profits discounted by the factor rho. The discount factor rho is between 0 and 1 such that firms value future profit less than the current profit. Now, for the sake of simplicity, assume that the demand intercept parameter A and the slope parameter B are both 1. There is no marginal cost. Then we can see that the one period of payoff for the firm 1 and 2 in each scenario can be expressed in a simple payoff matrix shown in the table. The table shows the one period of payoff associated with each strategy pair. For example, both firms payoff of 0.12 if both firms produce collusive output level. If firm 1 deviates and produces Cournot level of output, then the firm 1 gets 0.14, while firm 2 gets 0.10, and so on. The question here is, what strategy sustain collusion if the one-shot game is repeated infinitely many times, where the two firms interact over time? It turns out that so-called trigger strategy could sustain collusion in every period. This strategy says that firm I produces collusive level of output in every period unless its rivals deviates. If the rival deviates, then the firm I produces Cournot level of output forever. To see that the trigger strategy indeed sustains collusion in equilibrium, let's check that the profit under collusion and the profit under deviation. If both players stick to collusive level of output, the firm 1 gets a profit of 0.12 every period, and so the lifetime profit is 0.12 times 1 over 1 minus rho. Now, if firm Y deviates today, then the rival plays Cournot level of output from today on, and so the firm I gets 0.14 today and gets 0.11 from tomorrow on. We can compare the lifetime profits from the two scenarios and derive the range of discount factor where deviation is not profitable for firm I. We find that colluding in every period is optimal for firm I if the discount factor is high enough. And this result should be quite intuitive. If firms are myopic and cares only about today's profit only, then the firms will deviate today. But on the other hand, if the firms care about future profit, then they want to collude in every period to have a large future profit.